Okay, it looks like we're going here. You know what? I better. That's. Let me look and check. Yeah, it looks like we're going. Okay, fine. So next example. So here we want to compute an integral in the xy plane. We've got a domain. It's a square with certain vertices defined. The vertices are given 1, 2, 3, 4. There's our 4 vertices. And here's what that looks like. Here's that square. And it is not parallel to the axis. It's a tilted square. And now how in the world, right, if we slice this up, without change of variables, if we just sort of straight up do it, then we're either going to have this situation where we get 3 chunks, or we're going to have this situation where we get 3 chunks. One way or the other, we're going to have 3 chunks, and that's, highly undesirable. Let's hope for better. So here's the big idea. Notice in this question, I did not give you the change of variables function. Right? This first example that we did, I gave it to you right here in the statement of the question, just to kind of get our feet wet, to see the mechanics of how to use change of variables. But here, no such luxury. So how are we gonna? And how would I view this tilted square as being an image of a more desirable domain? And easy case. Well, I could untilt it. How about that? Right? That's a more desirable domain. And I can view this tilted square as being the result, the image of what you get when you take this untilted square and tilt it. If you rotate it counterclockwise by the appropriate angle. So that's the idea. We're going to have this G right here is just going to be the appropriate counterclockwise rotation. And reminder, back in chapter 3, we saw how to do counterclockwise rotations around the origin. Okay. So a couple of details have to get worked out. I mean, you've got to think about what is the appropriate angle, and this point was square root of 3, 1. So we can make a little triangle here. Square root of 3, 1. That makes that 2. This is a familiar triangle, and this angle here is pi over 6. Everybody on board? Okay. So call back to chapter 3. Now I'm going to let y'all do that on your own. All right, with the angle being pi over 6. Go back to chapter 3. Remind yourself of what the formula is for a rotation matrix. If you've forgotten, remember how you can rederive the formula for rotation matrix. The first column is just the appropriate rotation of E1. The second column is the appropriate rotation of E2. You can rederive that on your own. Right? You don't really have to go back to chapter 3. Anyway, for your consideration. So there's our change of variables function. Right? And written more explicitly, here is how that gives x and y as functions of u and v. And you can compute that Jacobian. And you can take that determinant, and details y'all can check on your own. And in kind of an eyebrow-raising result, we get that the Jacobian determinant is 1. Now, before I go on, let's take a quick pause and try to figure out what happened. Is this a coincidence, or is this natural? And I claim it's pretty natural. Let's recognize, after all, this G function, all it does is rotate. And when you rotate, things don't get bigger. They don't get smaller. Right? Rotating preserves areas. So the stretching factor really should have been 1. Right? Now this is as it should be. Everybody on board? Okay. On a test, quick reminder. I still want to see the calculations. Unless, look, you can ask me during the exam, is this one of these situations where, might we not need to do that calculation? You can ask. But most of the time I'm going to want to see that. Okay. All right. And then everything else is, pretty much just details. Remember, I've got to plug in for what x is. X is that, right? Y is this thing. So all I'm doing there is plugging in. Reminder, what do you plug in? The things that you plug in for x and y are given in the change of variables function. The change of variables function tells you exactly how to plug in for those things. So that's always where you look. Find the change of variables function. That's your source for plugging in. Don't forget your stretching factor. Right, our stretching factor that we computed here. Just 1. And notice that we have now successfully turned a dx dy integral into a du dv integral. In fact, a really easy du dv integral. And so it's all downhill from there. Everybody happy? Okay. All right. Okay, here's another example. Now this one looks really hard. It ends up being not that bad. So the question is going to be that we want to compute some sort of an integral over this domain that's bounded between these 4 curves. And this looks so ugly. Now, where did this question come from? It is, you may be wondering, this was the creation of a sick mind who was just looking for something ugly to make our lives difficult. Right? And I can see how you might think that. But for one thing, this is a standard example in change of variables, but I can tell you a natural place that this comes up. If you were to write down there's some calculations that go into computing the efficiency of the Carnot cycle. This is a thermodynamics thing, right? You end up doing an integral on a domain that looks really very similar to this. It's not exactly this, but it's very similar. So this is something that has this kind of thing does come up where we have different curves, 2 curves that have kind of similar equations. Xy equals one thing, xy equals another thing, and then another 2 curves that also have you'll notice similar equations. All right. And anyway, this is like I said, this is a real story. Okay. So what are we going to do? This is not a question where I would expect you to come up with the following realization on your own. This is a question where once I show you the trick, I expect you to be able to do it again. All right, so I'm going to show you the big trick here. This is a very clever idea. I wish I'd thought of it. I didn't. Somebody showed me this. And the idea is this, to say, okay, well, I have, in fact, a function of x and y that seems very naturally connected to this question. Wow. And I have this other function of x and y also very naturally connected to this question in the algebra, the statement of this, the problem that we're looking at. These are functions of x and y. Right? I'm going to use those things to define u and v as functions of x and y. Okay, functions of x and y. So instead of writing x and y as functions of u and v, I'm going to go backwards. I'm going to write u and v as functions of x and y, and those formulas are u is xy, v is xy squared. And so you complain, hey, you can't do that. The function's got to go this way. I need for my domain to be the image because I need to do a pullback. And okay, well, yeah, sure, fine. I guess that's kind of true. But think of it this way. Think of it as the pullback is, okay, it's a way of turning one integral into another integral, but another way to think about it is a pullback relates 2 different integrals. And if this integral is equal to that integral, then that integral is equal to this integral too. It's not really a one-way thing. It's here's 2 things that are equal to each other. Okay. So this is going the wrong way, and we're going to have to deal with that appropriately, but still, we can use this to relate the integral we have to a different integral, and that's all we really need. Okay, so more details. What is this new domain over here on the left? We ask. And one at a time, I'm going to look at these curves and ask what do they look like on the left. This curve here has equation xy equals 6. When I push that by this h function, when I push it over into the UV plane, what does xy equals 6 look like? Well, wait a second. Xy is u. So this becomes u equals 6. Which is that. Straight line. Okay, likewise, xy equals 10 becomes u equals 10. Likewise, this curve and this curve, xy squared equals 5, xy squared equals 7. Well, those are just v equals 5 and v equals 7. If you think about it. Right, this equation and this equation, if v is equal to xy squared, that's what you get. So, nice result is that this function here turns our highly undesirable, I don't even know what to call that thing, domain into a rectangle. Everybody on board so far? Okay. All right. So, yeah, but how do I'm supposed to plug in, right? Everywhere I see x and y, I'm supposed to plug in for how to write that in terms of u and v. And my function's going the wrong way. I don't have x and y as functions of u and v. I have u and v as functions of x and y. So that's an annoyance. And that is something that can be awkward. But what you do have is algebra relating the two. And so you look for the opportunities. One way or the other, you've got to figure out how to rewrite your x's and y's in terms of u's and v's, given these relationships. It's just a algebraic, bother. But it's still doable. Okay. What about the stretching factor? Let's write down what we know about the stretching factor. Here's what we know about the stretching factor. This h function, now you got to keep in mind, it's going the wrong way. It's giving me, as outputs, it's giving me u's and v's. H turns x's and y's into u's and v's. That means the stretching factor of h is what you multiply by xy area to get uv area. That's this. This is just, ignoring the fact that this is going the wrong way. Output area, the output from h is in the uv plane. Output area is the stretched out input area, which is in the xy plane. But this is not what we wanted. Right? I need to know area in the xy plane. I need to rewrite this thing here in terms of UV area. So, okay, go ahead. Right? You just solve for the thing that you need. And there it is. You just you get this slightly different formula. Geometrically, here's a way to think about it. If the function h that goes the wrong way, if it is stretching things out to make them bigger, then the action of going backwards is just going to do the exact opposite. It's going to squish. However much it stretches go to the left, that's how much it squishes going to the right. That's a different way to think about that. Okay. Alrighty. So anyway, as it turns out then, we have everything that we need, and here's how the algebra works out. Here was our original integral that we were interested in. Our stretching factor is 1 over v, because the Jacobian determinant of h was v. Yeah. X squared y cubed. What am I going to do about that? What is this x squared y cubed thing? Well, a little bit of playing around. Let's see here. Let me write my formulas. Here we go. I have this, and I have that, and I would like to know what is x squared y cubed. The reason I want to know x squared y cubed, again, is because that's my integrand. There it is. I need to know what x squared y cubed is. It'd be nice if I had x equals and y equals, but I don't. It goes the other way. But notice, you can just start to play a game, and the game is, I have xy and I have xy squared. What would I do to xy and to xy squared? How would I kind of combine them together to make x squared y cubed? And in this case, it's not a hard game. You can see if you just multiply xy times xy squared, you get x squared y cubed. In other words, x squared y cubed is uv. Yeah? Everybody on board? The how this is going to play out will be different in every example. It's not always going to be, oh yeah, you just multiply them, right? If these functions are of different algebraic sort of a structure, then you might have to add them, or who knows, right? But some form or another of playing around with them should get you what you need. Okay. All right. So I don't know why I erased that. That was perfectly innocent. Okay. So x squared y cubed is uv. And here we go. We have now written our integral. Everything's in terms of u's and v's, and we've rewritten our integral in the uv plane over that nice, pretty rectangular D, and it's all downhill from here. Okay. Yeah.
How did you know to assign u to uv to x, y, and v?
Yeah. So how did I know to create this function? Yeah, because I saw someone else do it, and I thought, wow, that was clever. And then I remembered it.
But
yeah.
In other cases.
Yeah, in other cases. So the trick to learn, the takeaway from this is that when you have a domain that's defined in terms of curves where the equations have sort of a pattern to them, then those equations, the algebra that's in those equations, and let's think it through a little bit more carefully. It's not the equations themselves that I define to be u and v, right? It's the functions whose level sets give me the equations. And I need it to be the functions whose level sets give me the equations, because I need, when I plug in this to be u, I need those to be lines. Right? So I need function equals constant, aka level sets. Does that make sense?
Yeah, so could you potentially switch them?
Totally. Yeah, sure. There's no magic here as to why this one's u and this one's v. If you would go the other way, totally fine. Yep. Okay. All right, so it's kind of a tricky little example, but nevertheless, if you all find yourselves in a circumstance where, again, the domain is defined by equations, then you can think in terms of having your change of variables function going backwards and adapting appropriately, and it's a good way to deal with it. Okay. By the way, there's a notation I want to talk about here. You may recall we wrote down. I hope we did. Yeah. So this was a while ago. Yeah, I hope we did this. Maybe y'all can remind me. Did we write down this notation, partial x comma y, partial u comma v, as the Jacobian determinant? Oh yes, I'm sorry. Of course, I remember now. Yeah, yes, it's. I made a mistake. I glossed over that as we were going through this in the development of change of variable. Let me go back to that. Sorry. Yeah, I have it written down here. I forgot to mention it. That Jacobian determinant is shorthanded like this. And different ways to think about, why that would be, but largely keep in mind what this is. The Jacobian of this function g it's a matrix which is the partials of the output variables with respect to the input variables. So this partial xy over partial uv, this is kind of suggestive of where all the elements of the Jacobian matrix come from. Right? So this is pretty natural notation. Now, awkward Jacobians of matrix. This looks like a fraction. Fractions aren't matrices. Fractions are numbers. And that's awkward. But notice, we're not interested in Jacobian directly. We're interested in the determinant of the Jacobian, and that determinant is a number. So this is pretty plausible notation. It ends up being that it's actually super convenient. So we're going to use this a lot. The Jacobian determinant can be written as a, air quotes, fraction, partial output variables over partial input variables. Okay. Sorry, I spaced and I forgot to mention that earlier. Okay. Let's see here. Let's go back to where we were. Yeah, here we go. So here is that equation again. This is the determinant, absolute value, of the Jacobian. There's that. Okay. What we argued on the previous page was this. If you're going the other way, if you want to know what do you do to UV area to get XY area, you divide instead of multiply. Right? And notice, it's like this is behaving like a fraction. So our motivation to write this as a fraction initially was that, the individual elements in that Jacobian matrix were partial derivatives, which we sloppily write as fractions. But then you assemble as a matrix, you take a determinant, the resulting thing is not a fraction. But now we see that even though that Jacobian determinant is very decidedly not a fraction, algebraically it behaves like a fraction. And that's a great trick. This is really convenient. You might say it's even a better idea. You just, use this notation for your stretching factor instead of Jacobian determinant, because it will keep track for you of whether you should divide or multiply. It's, and I cringe a little bit inside when I do this, but it's as if those cancel to give me that. And again, oh my gosh, you can't, that's not a real cancellation. These aren't fractions, and oh my gosh, you can't do that, right? But this is, you might call it a victimless crime. It's definitely a crime. That's definitely not okay, and yet it pushes you in the right direction. Okay. Likewise over here, it's as if we sort of have to divide because I need this to cancel with that, and this being in the denominator of the denominator, it's like it's in the numerator as it should be. Okay. All right. Victimless crime. Okay. All righty. I'm going to do the briefest of hand waves at how to do change of variables in 3 dimensions, because it's the same. It's so the same. So I'm going to go through this real fast. But suppose you have this solid in 3 space. You want to do a triple integral over this solid. The mind reels at how many different corners you hit and faces you sideswipe, and how to if you were to actually do this the old-fashioned way, slicing this up perpendicular to x, y, and z axes in whatever order, it's going to be a horrific nightmare. Right? Okay, so we can't do that. So what if we can view it as being an image? If we can view that horrific thing as being the image of a box, we can do a pullback. All I have to do is know what this function is and figure out what the appropriate stretching factor is. How am I going to compute the stretching factor? I'm going to compute the volume of that parallelepiped and compare it to the volume of this box. And the factor by which yellow multiplies to get green, that factor will be our volume stretching factor that we insert to make things right. That yellow box, little sub box, again blown up large for visibility purposes. And then here's the parallelepiped that it turns into. Right? What's the relationship between these volumes? Well, I just need to be able to compute the volume of this parallelepiped defined by these three vectors. These three vectors being the images by the derivative transformation of these three vectors. Just like the two-dimensional case. Right? So, just like in the two-dimensional case, these are E1 du, E2 dv, E3 dw. Their images are, well, what does the derivative transformation do to them? Just like in the two-dimensional case, what the derivative transformation does, scalars can factor out. The remainder is a partial derivative, just like in the two-dimensional case. So that gives me three edge vectors for a parallelepiped. The volume then is that determinant. You notice the common factor. Every term in this determinant is going to have a common factor of du, dv, dw. Notice the analogy? Notice how this is like it's the same thing, just with three variables instead of two variables. All you're left with then as a stretching factor is this 3x3 determinant. Again, in wow, what are the odds? The matrix that I'm taking the determinant of is exactly the Jacobian matrix. I mean, it really plays out exactly the same way. Right? So that's why I'm being quick through this. Nice punchline right here. Wow, it doesn't even fit on the page when I zoom. Okay, I'll back up. Okay, so X, Y, and Z are G of U, V, and W. Output area is a stretching factor times input area. So, said differently, don't forget your stretching factor, pull back at your will. Right, nice way to think about that. Yes? It can be any shape. Yeah, it doesn't even have to be a rectangular box. It can be any shape at all. I like to start with rectangular boxes just for motivation, because then you can see why we want to, right? But it doesn't matter what the pullback domain is. Yeah. Mm-hmm. Yeah. Okay, so I'm going to let y'all read the rest of this R3 discussion. I want to go on to the next thing, symmetry theorems. These are really powerful. We're kind of done with change of variables, by the way, except for this last little bit. So, just so you know why we're about to do this. Some textbooks don't talk about these theorems. It blows my mind that they would not talk about these theorems based on my own experience. So here is my experience, right? I did double major math physics. I spent more time on my physics than my math. That's how it worked out. Anyway, no surprise. As part of my physics major, I did bazillions of integrals. Bazillions. A lot of y'all are engineers. You're going to be doing lots of integrals yourselves, right? So get ready for it, right? Okay, so those integrals that I did, I have thought about it and just kind of, back of the envelope, just kind of estimating, just, what did it feel like? I think about 20% of the integrals that I did were susceptible to this argument that I'm about to show you. And this argument is super convenient, right? I'm going to cite a symmetry, what's called a symmetry theorem. it turns out that a lot of integrals, just due to the symmetry of the situation, a lot of integrals are obviously zero. Right? So now let's think about the details of why that's true. We'll get to that momentarily, right? But let's think about the magnitude of the importance of this. I took an entire physics major. I don't remember how many classes that was. Let's say 8 or 9, something like that. It's a fair number of classes, right? There's a lot of classes you have to take for a major. They were full of integrals. I'm saying that about 20%, I think that's a conservative estimate, but 20% of the integrals that I encountered, I could say, oh, that's zero by symmetry. So that's nearly 2 entire courses worth of integrals that I got to just, oh yeah, that's zero by symmetry. Right? So that's a huge deal, right? So what I'm going to show you in about 10 minutes here could save you, depending on how many integrals you encounter in your future, an entire course's worth of effort. And that's just while you're an undergrad. Of course, obviously, when you get out into grad school or industry or some form or another, who knows how much benefit you might get from this. So I'm a big fan of these theorems. I'm going to start off with this one that y'all have seen before. I hope you've seen this before. But if you have an odd function is a function where if you put in negative x to the input, then you get the negative of the value of the function as the output. I don't remember seeing this before, but they call these odd functions because odd values of n here make functions that have this property. Okay, if you have an odd function, this integral is 0, which is awesome. Now, do notice the domain has to be symmetric, right? It has to be an integral from negative a to positive a, right? So, but if the domain is symmetric, if the function has this odd symmetry, that integral is 0. Now, how cool is that, right? Imagine, what if this function here is going to require you to do some trig substitutions or integration by parts twice or, some hairy, nasty, integrals can get super ugly, right? Isn't it nice to just be able to say 0 by symmetry? Awesome. Awesome result. Okay. All right. So I'm going to show you multivariable versions of this. So I do have to define a couple of things. This is just details, words that have to get said. The reflection over a line. This means exactly what you think it means. Here's a picture. If you have a line like that, a reflection over the line of this point is this point. So, in other words, if the line were a mirror and if x were a person looking in the mirror, then the reflection is where that person's reflection would appear to be in the mirror. Right? Very natural terminology. Okay. So that being said, we're going to talk about what it means for a domain to be symmetric over the line. Symmetric over the line, let's see, do I have a good picture here? I guess I don't. Okay, I'll draw a picture. What it means for a set to be symmetric over the line is that whenever a point is in the set, the reflection is also in the set. And whenever a point is not in the set, then the reflection is also not in the set. So it's a Rorschach diagram kind of thing, right? But this is what it means for a set, a domain, to be symmetric over the line. I think it's a pretty natural definition. Everybody on board with that? Okay. All right. And now we're also going to define what it means for a function to have odd symmetry. A function has odd symmetry over a line if, and notice we're just ripping off, we're trying to steal, shameless, I'm trying to basically plagiarize this theorem in the two-dimensional context, right? Odd symmetry means that when you reflect the input, we want to get a negative in the output. Okay. All right. Totally analogous definitions here in 3 dimensions. Reflection through a plane, over a plane. means this picture. Let me draw the picture real quick. If you have a plane like that, a reflection of this point means that you go perpendicularly, you get that point reflecting through the plane. So again, exactly what you think it means, right? Reflection through a plane. And very similarly, a set is symmetric over the plane if, again, exact same thing, right? A function has odd symmetry over the plane, same deal, reflections give you a minus sign in the value of the function. Okay, so these are just definitions. With these definitions having been made, here is the big result. I'll come up to that in a second. If you have a domain that's symmetric over a line, this is for any integral in R2, by the way. If the domain is symmetric over a given line, if the integrand has odd symmetry over that same line, congratulations, your integral is 0. You don't have to slice up anything. You don't have to think about outside bounds and inside bounds and what's a constant and what's a variable and antiderivatives and all the whole, f of b minus f of it, the whole shebang. Integral 0. Awesome. Yeah? Everybody on board? Okay. I'm saying 20% of the integrals that I saw in my physics major were 0 because these conditions were satisfied, and therefore, integral is just equal to 0, and I didn't have to crank it out. Okay. All right, now there is a very, very big point here. It is essential that the line over which the domain is symmetric and the line over which the function has odd symmetry, those have to be the same line. This is not a issue of formality. The theorem is dramatically, catastrophically false if you're not careful to that point, right? It's got to be the same line. Okay. Show you a quick proof. We have about 5 minutes left. Quick proof. First observation I'll make is that when you do a reflection, the stretching factor is 1. Now, I don't want to prove this. It's a little bit of a sort of a digression, but I think this is pretty easy appeal, right? If you have a flat mirror and you look at yourself in the flat mirror, that's the same. That person's the same size as you are, right? I mean, reflections. If you do this, it doesn't change the size. I think it's an easy appeal, right? Okay. Let me show you how to prove the result. I'll show you the three-dimensional version also, but I want to prove it first. So we are supposing that we have a domain that's symmetric and that we have a function that's odd. So first observation, because the domain is symmetric, when you reflect the domain, you get the same domain. It is, after all, symmetric over that line. Okay. So if you're looking at an integral, I can view the domain as in fact being its own reflection, because it's a symmetric domain. All right. Now we're going to look at this integral here, and we're going to do change of variables, which is why this discussion's in the section on change of variables. We're going to do change of variables here. After all, notice we're looking at an integral where the domain of this integral is an image. It says right there, it is the image through R of this other domain. Happens to be the same domain, but this is, let's say, other domain D. Okay, so doing the pullback, here's how we do pullbacks. We pull back to the pre-image, also D. Right? We've got to plug in the change of variables outputs are functions of the change of variables inputs. They are the change of variables function of those inputs. Don't forget your stretching factor, which, by the way, we just agreed was 1. Right? And we have here the this is the change of variables on okay. So let me finish this one little bit here, and then we'll be right with y'all. So we've done the change of variables to get down to this equation, and it's basically all over but the shouting here. That, as we just noted, is 1. The function is odd. So f of the reflection is the negative of the otherwise value of the function. This minus sign pops right out like that. And look what we've showed. We have showed that this integral is the negative of itself, and therefore that integral has to be 0, which is what we wanted to show, right? So this is it's not a hard proof. It's an immediate application of the change of variables theorem that we've been working with. And when you check your conditions, you get to just declare your integrals to be 0. Okay, this makes a good stopping point. Let's call it a day. And, see y'all later.